Hello, IB students. This lecture, we're going to look at uniform acceleration. All right, so in the last class, we've introduced about acceleration. It is defined as the change of velocity of an object in a given period of time. All right, so if an object is going through uniform accelerating motion, it means that it's accelerating at a constant rate throughout this time span. All right, so we've introduced to you the VT graph in the last lecture. Well, if an object have a uniform acceleration, its graph on the VT graph should be a straight line because only the straight line have a not changing slope. The last class we've talked about how the slope of a line in the VT graph represents the acceleration of that object. If our acceleration is constant, is uniform, we can only have one slope, which means the line is straight no matter if it crossed the origin or not. So, it can have a y-intercept. So, for example, this is our object, all right? So this is object 1. It's currently experiencing through uniform accelerating motion, all right? So this is its initial velocity, maybe 5 meters per second, and maybe its acceleration is 5 meters per second. So this is 10, this is 1. So to calculate the acceleration we've talked about, we just minus the change of velocity, which is 10 minus 5, and we divide it by the change of time, 1 minus 0, which is 1. Okay, so we got our acceleration, which is equal to 5 meters per second, which is 5 meters per second squared, all right? So if you don't know what this quantity means, just go back and watch my last video. So these are the recap from last video. And today, we're going to figure out the SUVAT equation system for accelerating motion, all right? So it's a set of 5 equations, which is describing uniform acceleration motion, very important. The first equation, let me write that down actually. The first equation is A equals final velocity minus initial velocity divided by time equals acceleration. That is the defining equation, which we've also introduced in the last lecture. It is defined that way. It cannot be false, all right? We have the equation for acceleration. What is the equation of velocity going to be? Say I want to calculate the velocity at t equals 2 seconds. How do we do that? Well, it's very simple. Since we know the acceleration and we know how long it has accelerated, we know how fast that the object has changed from the start of acceleration to the end of acceleration, right? So basically, at the start of acceleration is t equals 0, and the object accelerated at 2 seconds, and its acceleration is 5 meters per second squared. So we can use that to calculate its change of velocity, which is just a times t, which in this case is 2 times 5. This means from t equals 0 to t equals 2, the object have changed 10 meters per second. Its velocity goes up 10 meters per second, all right? However, if I want to calculate the actual velocity at t equals 2, I need to take account of the initial velocity at t equals 0 before the object even starts accelerating. So I need to plus the initial velocity, which is 5 in this case, and get our final answer, which is 15 meters per second, which in this case is the velocity we want to calculate. So, this equation is just the reforming of that equation. We're just moving t to this side. We're moving v initial to that side. We got our final velocity equals initial velocity plus acceleration times time. All right, so that equation, you don't need to memorize it. You just need to understand. Well, how fast I am moving right now is just how fast I've moved before I start accelerating times how fast I'm accelerating and how long I'm accelerated, right? So this is a very intuitive equation. You just need to understand deeply about the concept of velocity, time, and acceleration, and you don't need to even memorize this formula, all right? So this is our second formula. All right, so the next thing we're going to investigate is going to be a little bit complicated, all right? So we've talked about the relation of acceleration to velocity, v equals at, right? And we've also talked about the relation between velocity and displacement in our first video, which is d equals vt. Well, how do we combine those two equations and make a relationship between the displacement and the acceleration of an object? So let's do that. All right, so we know that v equals inertial velocity plus a times t. All right, so d equals d naught plus vt, right? So that's our equation we've talked about in the first video, and I've said that d naught will not appear in most situations. D naught is the initial placement, however. So this will not appear in the most situations, so let's just erase it. So displacement is equal to velocity times time. Well, how about that? We know the equation for velocity. We just plug that in. It equals to initial velocity plus acceleration times time again, which is equal to initial velocity times time plus acceleration times time squared. All right, time squared. Is this equation the actual equation that describes the acceleration and displacement? Well, no, we've made a crucial mistake, because in this formula, the underlying assumption that is v is constant. All right, so only if v is a constant value can we just use this equation once. However, as we know, we are now in the uniform acceleration motion. Our v is not constant. So we need to make some adjustment to this equation. Well, how do we adjust it? That's kind of related to calculus and integral, all that kind of advanced math stuff, which I'm not going to introduce here. However, the result for our adjustment is to add a little 1/2 is add a little half on the front of acceleration times t squared. All right, so this is our final equation for displacement. Well, a lot of students are now complaining, how about that, Mr. Wavy? You say don't memorize the formula, understand them. How do I understand that? That's literally so freaking complicated. All right, so don't worry, that's easy. We'll look at that together. All right. So let's look at the geometric representation of this formula on the VT graph, right? So for example, I want to calculate the distance or displacement of the object, our object between 2 seconds, between t equals 0 and t equals 2. Well, what do? Well, my d is equal to vit, which is my initial velocity times time. Well, my initial velocity is 5 seconds. The time I've traveled is 2 seconds. Well, what's the initial velocity times time? It's just this rectangular area, right? So this rectangular area is VIT. It's literally VIT. So what about 1/2 AT squared? All right, so 1/2 AT squared. What is it? Well, it is just 1/2 times AT times T, right? So what is AT? Well, AT is equal to delta V. Well, it is the change of velocity between t equals 0 and t equals 2. It's this length, and t is this length, right? So t is a change of time. We've talked about it. So it's literally just equal to AT, which is this, times t, which is this, divided by 2. So what is that area? Well, it's just this area, right? So it's a triangle. Remember the formula for triangle? 1/2 AH, all right? So we've known that the displacement of an object between t equals 0 and t equals 2 is just the area under the straight line, the area under the curve between t equals 1 and t equals 2. And more specifically, it's just the area of this tripod, right? And how do we calculate the area for the tripod? Well, we divide it into 2 sections. First, a rectangular section, and second, a triangular section. And these 2 sections basically represent the area, corresponding of the rectangular and the triangular section. So this is the geometric intuition for the formula. So having had the geometric intuition, we can understand the formula even more deeply with one explanation. All right. So my displacement, forget about acceleration. If I don't have acceleration, if my acceleration is 0, do I still displace in those time span? Well, I do, because I have my initial velocity, right? So the least amount of, displacement I would have is just my initial velocity times time. Well, in that case, my acceleration is 0. I'm going through uniform motion, right? So VIT is basically the underlying displacement I have, no matter if I have acceleration or not, right? So this VIT, that portion of displacement is it's only merely a result of me having the initial velocity of 5 meters per second. And however, right now, I am doing uniform accelerating motion. So I also need to calculate the displacement due to my acceleration. All right. So, well, how do I do that? I don't know. I don't know how to do that. But one thing I do know is that right now I have, right now, I don't need to take account of the initial velocity because I've already written it down, right? So I'll just pretend that I don't have any initial velocity. Well, how do I calculate the displacement due to my acceleration? Well, it's simple. One thing I do know is that my final velocity is equal to my acceleration times time, right? So why? Because I don't have any initial velocity. So I will just use the final velocity to time the time. Right, this is my final velocity. This is my final velocity. I will use it to time the time, and that essentially gives me a overestimate of my displacement due to my acceleration. Because my acceleration, I'm going from a low velocity to a high velocity in a given period of time whilst traveling distances, right? So, and now I'm estimating that for the whole time, I've just traveled at the maximum as the final velocity and times time. Well, that is obviously going to overshoot my actual distance. And since I am doing uniform acceleration motion, that overshoot is precisely 2 times the actual displacement I have, because VI, VF in my case is just this length, and I've timed it to t, right? So I've got this huge rectangular area. However, since I am accelerating uniformly, I can, simply and conveniently divide it by 2 and just get this actual area, right? So the second section will be 1/2 times VF plus times t, and my final velocity is just 1/2 times AT times t, which is equal to 1/2 AT squared. This is the explanation of the formula of these distances relating acceleration. All right, so it's very important you should memorize it. Or no, you shouldn't memorize it. You should understand it intuitively, in your heart, deeply. Because 100 years later, if I say what's the acceleration and the displacement, what's the relation, you should call it out in 1 second. All right. So let's now look at a work example of this. All right. So this is Newton's apple tree, very famous in physics history. All right. So the apple and Newton's head, they are 1 meter separation. And now the apple suddenly loses connection to the tree and it starts falling to the ground. And why do it fall to the ground? Because, well, it experiences gravity. And the acceleration due to gravity is constant. It is 9.8 meters per second every single second, all right? So this is the acceleration due to gravity, 9.8 meters per second squared. And right now, the separation is 1 meter. And I want you to calculate how long have the apple fall until it hit Newton, right? Well, we can just use the formula of time. Well, it's final velocity. Well, actually, we cannot because we don't even know the final velocity. However, we do know that we can use the fourth formula because we know the distance. Well, let me just write the fourth formula down first, equals 1/2 AT squared, because the distance is just the height between the apple and the person's head. Well, it's just how long the apple is going to travel, right? So the distance is just the height. It is equal to V initial. Well, the apple is hanging stationary on the tree, so it doesn't have any initial velocity, so it's 0. So this term, don't need to look at it. It is equal to 1/2 times acceleration of the apple, which is the same as the acceleration everybody experiences due to gravity, no matter it's a hammer or a feather or you or me or apple or the moon. We all experience 9.8 meters per second of acceleration due to Earth gravity. All right, so times g, well, that is a constant. We denote it by the letter g. All right, times time squared. So what do I want to calculate? Well, I want to calculate how long the apple have fallen. Well, I just rearrange this equation. I move the 1/2 to that side. Well, it equals 2h. Divide both sides by g and take square root by both sides, and I get t is equal to the square root of 2h divided by g. Well, it is equal to 2 times 1 meter. Oh, I'm sorry. It is equal to 2 times 1 divided by 9.8. I just approximate it as 10. All right, so it is equal to 5 over the square root of 5 seconds. So that is how long the apple have fallen. And now I want to calculate the final velocity of the apple. I want to calculate the how fast the apple hit the Newton. All right, so basically a measure of how painful is it that Newton experiences. All right, so we will just use the second velocity equations. Well, we know the final velocity is equal to the initial velocity plus acceleration times time. And I don't have any initial velocity. My apple is hanging on the tree. Well, my acceleration is just a g. And my time is still time, right? So it is just equal to 10 times the time I've already calculated. It's 5 over root 5 seconds. So when the apple hit Newton, its velocity will be 2 root of 5 meters per second, which is approximately 7 seconds, I think. Well, that's a huge velocity. Newton is going to feel very painful after that. All right, let's look at our final equation of the day. So, as we've talked about before, displacement equals velocity times time will only be useful if velocity is constant, which means the object is going through uniform motion. All right, not uniform accelerating motion, uniform motion, because we can just plug the one value of velocity into this equation and calculate it. And we talked about if the velocity is changing for different objects, we need to analyze the situation based on what we are facing. However, there is still a formula that works no matter how crazy the velocity is changing for the object. Well, that equation is displacement is equal to the average velocity times time. Because think about it, when I'm traveling fast, I cover a lot more distance, and when I'm traveling slow, I cover a lot of smaller distance in a given period of time, right? So my velocity is going fast, my velocity going slow, fast, slow, fast, slow, fast. So the final distance that I've covered should be just equal to if my velocity is the same on the average level, right? So that makes sense, and you can actually prove it. I will leave it to a homework to you to actually prove that this is true. So no matter the change of velocity, if I can somehow calculate the average of velocity during this whole time span, I can calculate the displacement of the object even with non-uniform accelerating motion, right? So this is a universal workable equation. However, right now our situation is far less complex than this wavy curve, right? Because today we're only investigating on uniform acceleration, right? My VT graph is a straight line, right? So when it's a straight line, well, I can calculate the average velocity between any two moments very easily. Say I want to calculate between 0 and 8 seconds. Well, this is the final velocity. This is the initial velocity. What's my average velocity during this period? Well, intuitively, it's just 4 meters per second squared. It should be the midpoint, right? So this is 0, this is 8, it should be 4 meters per second. Well, you will be right, because in uniform accelerating motion, average velocity is always equal to the final velocity plus the initial velocity divided by 2. So what am I essentially doing is I'm taking this, I'm adding it with the final velocity divided by 2. Well, this is just how you average everything, not just velocity. In math, kind of average number, they all use this formula. So it also applies to velocity, all right? So this is the case in uniform accelerating motion. All right, so my displacement can now be written as 1/2 of final velocity plus initial velocity. Well, what is time? Well, we've derived the time is final velocity minus initial velocity divided by 2. Divided by 8, sorry. So it's final velocity minus initial velocity divided by 2. Well, let's just combine those two equations together. And what do we get? Well, in the denominator, we get 2a. And in the above, VF plus VI times VF minus VI. Well, what is it? Well, it's just VF the final velocity squared minus the initial velocity squared. All right, so this is the equation I want to introduce to you. And in most textbooks, they rearrange the equation to make it feel like this. All right, so 2AD is equal to VF squared minus VI squared. So finally, this is our final formula of the day. All right, so it is a little bit harder to remember. But when you see this formula, when you see it on the textbook, you should know that the essence of this formula is just the displacement is always equal to the average velocity times time. When you see this formula, you should automatically depart it into two sections and reduce it back to its original form. This will help you to understand this formula without the need to memorize it. All right, so let's write it down. And you may notice that this formula actually does not involve time in it. So for all four formulas, we've involved time in our formula. However, this, we do not have time in it, so it will be a very powerful problem-solving tools. You know, if in the question you are not given the time of the object, you can just use our fifth formula. All right, so these five, they are called the SUVAT formula. All right, so this is the U formula. So these five, they are the SUVAT formulas. Do not memorize it. Understand, and understand it. If you memorize it, you have lost, because these five formulas will be repeatedly used throughout your physics high school career if you decided to choose this course, right? So it's very important. Do not memorize it. Understand it from a basic level. These five formulas, if you really spend time, they are very easy to understand. And that is all I want to say to you. Thank you so much for watching, guys. If you like this video, consider subscribing, and I will see you in the next lecture. Bye bye.